How's it going? Good? Good. How many of you have been working in Azure? More than 6 months? Okay, more than 12 months? Since 2008. Okay, so let's start with what we're talking here today is architecture best practices. So it's a couple of tricks since the early beginnings that I've been learning with basically banging my head a lot of times and doing some stupid things and trying to take the best out of the system. And some architectural patterns that really helped achieving that. So what we have here is a set of architecture or design considerations you should take, and a set of architecture examples that you can have. How many of you have used something like CQRS? Good, one. We're going to be talking a lot about CQRS. So to start off, one of the questions might be, who's this crazy guy? So my name is Nuno. I'm Director of Cloud Services in Ideologies Technologies, and also acting Europe CTO. And basically I manage anything that it's cloud, where we actually bucket the cloud. That big data without the cloud doesn't make sense, so big data is inside. Internet of Things, as internet needs cloud, it's there also. So it's a whole bucket of a lot of things. And Azure MVP and Service Bus Champ. Anybody knows and Service Bus? It rocks. As well as Azure. Okay, so if you really want to hear mumbling, there will be my Twitter and my blog. Every now and then there are some interesting things, and some other times no. So start off, what are we going to see? Design concepts for cloud solutions, critical design considerations, that's what we're going to do. Then Azure best practices, because it's important to understand when we are architecting something, we need to understand the limits. Would you agree? We need to understand the limits of what we are working with. And normally, what would you say is a good architecture? Is it the perfect architecture, the perfect scenario, or the best architecture which fits the business needs and the budget that we have to work with? What's the best one? First and second? Oh, one at a time. I couldn't hear anything. It's the second. Normally, the perfect world is one thing. What we need to deal with is a completely different scenario. So, and then some real life, highly scalable architectures and lessons learned. So, design considerations. What you should be thinking about is designing applications for the cloud, and the for the cloud is something we can discuss. If we actually are already doing multi-tenant applications, highly scalable, thinking about multiple different areas, so HA and so on, we are already architecting which will work perfectly in the cloud, right? Because if I'm already thinking, and when I architect something, even on premises, if I architect something which is already understanding if that I have two systems in HA, so I can fall back from one to the other, so I need to make sure that they sync in between themselves. So I'm already thinking about something which is going to help about the cloud. Because cloud is all about that. It's redundancy. It's ability for me to scale, ability for me to have redundancy, ability for me to have something which will allow me to scale fast, but also understand what's happening with the application. And if something goes wrong, immediately they will turn me to something else. But that's when things fail, right? And in the cloud, nothing fails, right? Correct or not? The cloud solves every single problem with machines in the world. So those things of machines crashing doesn't happen anymore. That's a myth. No. It's not a myth. Actually happens too often. The way we need to approach it is actually we know that it fails. So let's make sure that our application is fault tolerant. That's what we need to do. Because what the cloud does is provide redundancy, and when things fail, they will recover fast. But then our applications need to do the same. So in reality, what we're saying is the key element here is multi-tenancy. Multi-tenancy being resources in the platform, shared resources that I'm leveraging from different entities. That's the key thing. One of the things, and I've been working with the cloud for a lot of years and helping a lot of different customers over the years in leveraging the cloud. And one of the things is when we start the conversation, they go, oh, I want to move this into the cloud. And being that I'm a service provider and I provide services on the cloud, what would you think my next question would be? What do you think? What?
What kind of service?
What kind of service? Actually is not. What I ask first is, why do you want to do that? What's your driver? What do you want to achieve? Oh, I want to achieve agility. I want to achieve cost reduction. I want to achieve scale, whatever. Why is that important? We need to start with what's important for the business. What will be our tenets in order for us to start building our architecture around it? Because if it tells me my goal is to do cost reduction, probably I will have a different architecture than if it tells me what I want is to have decoupling in scale, right? If I want decoupling in scale, we'll decouple everything, we'll put in different machines and everything. That's potentially more machines that I have. If it tells it's cost reduction, hold on, let me start and try to get some of these things working on the same machine. If it's agility, then I'm going to target much more information about how's the application going and providing more automation around in order to provide that agility. If they are saying the reason why I really want to change is because I want to reduce my maintenance costs, then what I need to do is in my architecture, my elements which define how the telemetry in the application needs to be done needs to be a lot higher than in another situation. How many of you are familiar with the difference between telemetry and logging? So everybody is using logging. What's the difference? What's telemetry? What do you think telemetry is? How is it different?
It's stats about how the environments are running and analyze, I believe.
How the environments? So let's get an example. How many of you like Formula One or something like this? Nobody? I like it. It's pretty cool. So one of the things is you hear telemetry, telemetry, telemetry every single time. And you see some graphs and everything. That's the real-time information about every single part of that car. So they can do, because they have all that information, I have the telemetry exactly that specific sensor in that part is handling this much heat. So that means I need to tell my driver to be careful because his back tire is actually having overheating, and so he shouldn't try to continue to do the turns like he's doing. Things like that. So it's not me fetching the information, it's the device sending me the information about how's doing. And that's what the difference is. When we do logging, we define, is like saying, I did this, and I store it somewhere that actually, how many of you actually went through the logs? Apart from this whole thing blew up, how many of you went into the logs before that? Yeah. Same times as me. If it's not broken, don't touch it. You might break it. So telemetry is completely different. Is us putting, some of you were in my Internet of Things talk yesterday, and telemetry is all about those sensors and thinking of an application as a sensor which is feeding information about what's happening. Things like, I'm connecting to Azure storage. I failed. I took this much time. I failed again. It's a second attempt. I took this much time. Why is this important? Because now I can actually leverage that information and say, using some things like event-driven architecture with complex event processing and finding a pattern and saying, if, for example, during a period of 5 minutes, I have, in average, the time to connect to a storage account is more than 5 seconds, I'm facing a performance degradation. So I act by calling my PowerShell script, which changes the primary storage account to the secondary storage account. That's what telemetry can give you. The reason why cloud is so, I wouldn't say cheap, it's so competitive, and there's the market wars, is because of the levels of automation. How is that achieved? With telemetry. Does that make sense? Any questions so far? Okay, good. Not throwing things, so that's a good sign. So the other part is distributed systems. The cloud is nothing more than a very, very distributed system. I have multiple different elements. I have different services, storage, compute, can be cloud services, websites, VMs, can be Azure Media Services, mobile services, anything. It's a massive distributed system. How different is it from a distributed system that I have on my on-premise solutions, if I have a massive data center, when I have machines everywhere, and I need to make sure that the latency is playing a role? Is latency important when we are architecting this? No, of course not. Latency, there is no such thing as latency. Speed of light, pff. We all have fibers in our houses, right? Who doesn't have fiber in the house? Yeah, I don't. Inside the house, no. Outside, yes. Actually, in my previous house in Portugal, they actually placed fiber inside the house. I love it. It was so cool. The kind of things, kind of devices that I could connect was absolutely unbelievable. My wife didn't like that much. Don't know why. Abstraction. One of the things with the cloud, with designing solutions for the cloud, is also abstractions. Abstracting what I'm connecting with. So when I design to the cloud, and one of the things that a lot of customers ask me is, okay, but I don't want to be vendor locked in. It's a fair statement. I wouldn't either. But how do I do that? So I don't want to be vendor locked in, so I'm going to use infrastructure as a service for everything. Does that make sense? No. That is not the way for me to be not vendor locked in. It's an architecture pattern. If I leverage something like repository patterns, and I use and I implement different repositories that I'm using, if I'm using a repository which is Azure Storage, or if I'm using a repository which is a file system, I can leverage the best of the services and change at any time. Maybe at the first interaction, what I'm doing is actually just building one, but I already have the architecture ready to do that, right? So I need to consider that this is a massively distributed system, and I need to create the abstractions. The other part is the commodity. hardware at internet to scale. What do you think about the machines that are in data centers? They are all super machines, right? Yeah? No? Who thinks that they are the typical machines you would see on a data center? Anyone? Something like 256 gigs of RAM, a pile load of processors in a single box and everything, right? No, absolutely not. It's better to have, and that's one of the things we learn from multiple sites, like peer-to-peer sites. Never use them, for the record. We're on tape. So those peer-to-peer taught us something. A lot of small machines working together can do much more and faster than one big one. And the cost is completely different. So what we have is the internet to scale and commodity hardware. One of the first times I visited one of the data centers of Azure, I looked at some of the machines and I said, I don't have anything like this at home for several years, pretty sure. But in reality, those machines all together actually provide a very good system. And so we need to understand and we need to think about that. We need to think that, let's see an example. What would you prefer? Would you prefer a lot of different small machines, machines like a medium size, something like 3 gigs, 4 gigs of RAM, and have like 10 machines out of them, or have just 2 with more RAM, like 16? What would you prefer?
Does depend on what you're using it for.
Exactly. That was a tricky question. Depends what you're using it for. So I'm using it for a website which doesn't have any math calculation that leverages memory. So would I use, for a website, would I use a bigger machine or prefer more smaller machines? Probably more smaller machines. And the reason is because each machine also has, and then it's playing also because different machine sizes at different speeds in terms of the network cards. So playing around with those elements, it's what's going to allow us to choose the size of the machine. So, but normally, I can give you an example that in a small machine, in Azure, in a small machine, with a very optimized architecture. So with the normal architecture, you can have like 200, 500 type of requests per second. With a very optimized architecture, you can have about 10,000 concurrent requests. Isn't that cool? So do I need more machines? Only if I'm doing, for example, math calculation, things like I have a dupe in there. Do I need high RAM? Yes. There is a lot of calculations happening. I'm doing work with images and processing images. Do I need a lot of RAM? Yes, I need. And so that is where we are going to have. But normally, our first approach should be, why do I need a bigger? Let me start with a small machine, and then give me the reasons why I need a bigger one. Now Azure has 2 different series, the A series and the D series, whereas the difference is actually that the Ds have the SSD drives. So if I have, when will I use one over the others? I have a SQL server that I need to put in there. SQL server is a little bit is an understatement, IOPS savvy, right? So I need a D series. I have something which doesn't have almost IOPS. Do I need an SSD drive for that? Yeah, if you want to give a lot of money to Microsoft, they wouldn't bother. They would like it. They might actually send you a present and all if you do something like that. Another thing is it's composed by multiple services. This is what the cloud is. So when you design to the cloud, you need to think about multi-tenancy of the resources. So you're not the only one using that cloud. So behave. Okay? Distributed system, you have load balancing, you have systems which are not at the same location. So consider latency, where latency right now, if some of you know the infrastructure architects, things like DNLA is the typical architecture we have on most data centers. Microsoft changed to a Quantum 10 architecture, which has a backbone in the middle. It's a flat network architecture. So that means that the speeds went up about 10,000 times. So I have under a millisecond in any part of the data center, I can have under 1 millisecond communication. So latency in the same region is not a problem. But careful when you put the elements in the region, careful not to put, oh, my web application is in one region and my database is in another region. That might not end well. Not for latency, not for cost. Okay, so critical design considerations. So far, any questions? Comments? Personal attacks or other? No? Good.
Can I ask you mentioned SQL Server there?
Yeah.
You start dealing with systems that have got several instances of SQL Server floating around, you want to move into the cloud. Doesn't the architecture that you're thinking of get thrown out the window because of that? Because you can't get the data from A to B in quite the same way when it's in the cloud than it is if it's in your own data center.
So in that case, what you can do, for example, I have a system which we have about 1,000 SQLs that we have in the cloud. And we have most of them, most of those 1,000 machines are actually, they have like 3 replicas because in that case we wanted to achieve 5 nines. So I actually have 3 different machines serving the exact thing in HA with always on. So in that case, they can do whatever they want. They can change from machine 1 can go and die. And in that case, I don't only have the 3 machines that are in active with always on. I have another one which is in active passive. And so they can do whatever you want. In that case, it's not so much an architecture, a solution architecture, than what we're talking about, the infrastructure architecture and the topology I'm going to deploy it in. So in that case, yes, it's different. I need to consider that, which is one of the things when we go into the cloud is what's the SLA that you need. That's the most important part. So one of the things that I asked them was, what's the SLA that you need? And they said, I need 5 nines. And I said, monthly or yearly? And they said, monthly. And I'm like, huge. Are you sure? And he's like, yeah, I'm sure. Okay. This is how much it costs. Are you sure? Yeah, okay. It's cool. It was the biggest system I've done so far. So it has about 3,000 machines in the cloud. It's jumping to 6,000 now. And that's only the infrastructure. So yes, it's what it can happen is that the same topology, if you do it on-premise, is going to do the same thing. The difference is on-premise you have the backbone. The data center is normally smaller. So a data center, the Chicago data center I showed yesterday, it's about 60 football fields. So yeah, it's a little difficult if you don't have the right networking to get the right latency. But that's already covered for you. So it's the same, but it's a very important question to do. What's the SLA and why do you need that SLA? I had customers ask me, I want 5 nines. And we ended up with 3 nines, which was good enough because their budget was not that high. Normally, I like to give them options. Like, you want how many nines? 5. This is for 5, this is for 4, this is for 3. And they end up like, this one is good. Sounds good. I can deal with that. Because there's a lot of ways. And in the SLA part, you can play in a lot of different ways. One is, okay, the SLA is the full for the full system, or can I have so a degradation of service is acceptable. So for example, I say my SLA is 3 nines for 100% of the capabilities, but I can have a performance degradation of 50%, and I define which features they are, and this needs to have 4 nines. And this is the third part, which is if more than this goes down, I have a fallback in my SLA. And so you can create multiple levels, multiple type of services in order to provide that, in order to play around with the cost. Does that make sense? Okay, critical design decisions. 1, design for internet to scale. Failure is expected. It's not a surprise, it's expected. There's only one thing we know about a system. What is that? It will eventually fail. And normally, when you don't need it to fail, when you really don't want it to fail. So for example, yesterday I brought the car piece for my IoT talk. I connected. Just before it starts, everything was okay. I did the first part of the demo, everything was okay, and then it crashed. Right when I didn't need it to crash. So, typical thing. So, it's how life works. We need to deal with it. How do we deal with it? We basically create resiliency in our applications. We create, actually, we go and we can't have the typical consistency, availability, and partitioning. The CAP theorem, we can't have the 3. Choose 2, the one that are more important for you. So what I want to have is my system has to be always consistent and always available. Okay? Or I can use eventually consistent systems. How many of you have worked with eventually consistent systems? No? For example, let's talk about Amazon. Amazon, the web store, the online shop. So do you think they are consistent or eventually consistent? Eventually consistent. So I have what in 2007, I think Pat Holland called ACID 2, which was basically saying there is compensating model. So what they do is we all go and try to look for a book or something, and we see there are 3 in stock. And we go and buy, or even 1, there's 1 in stock, and we go and buy it. Does it actually check for the stock at that level? No. What's more important? What's their business about? Selling stuff. So what do they need to give priority? To the selling stuff part. So what do? They accept. We can be 1 or 3,000 at the same time asking the same thing. It's still 1 for everybody. So you basically go, it gets your order, goes through, and it gets on the message queue. And then it starts to get processed by the warehouse management because we have complete decoupling. It starts, the first guy, that is the lucky winner, comes up and the warehouse says, this, send. Then the next guy comes and say, yeah, sorry, I don't have any more in stock. What do? Basically then, that goes into a compensating queue, which goes and understands how much time will I take in order to get this order back. So it takes like 1 week, 1 day, 5 days, whatever. And based on that, there are several different compensation elements. So for example, one time I actually bought 3 books, and because one of the books actually, this happened, and it was 3 weeks until they returned me, they actually gave me credits, which allowed me to buy the other 3 books that I also wanted. And I was like, please, please get late again. Please, 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 I want more. But this is, in terms of the business, the cost of having that thing consistent versus the loss of not taking that order. It's much worse not taking the order. So we need to embrace eventually consistent. Do I need to have the system in real time, up to date, to the second, to the millisecond? How many of you work at systems would need to be under the millisecond or the second with the right information? If it's not there, if you do something, you enter something, you save, I need to see it there, or else someone will die. Maybe I did a project for a nuclear power plant, which was the emergency system. Yeah, that one was not eventually consistent. But we had a DR. One of my colleagues actually lived nearby the power plant. So actually, when we presented the DR strategy, it was a stepped approach. So several steps for the DR. If this fails, and everything. Who starts, who actions the alerts. And there was, actually, I added one slide when we were reviewing, actually with the customer. I added one slide, the last resort, what was it? It's, oh, one of our guys actually lives close by. If something happens, you will hear the bang and he can start off. And he was like, are you crazy? Yeah, that's also a way of actioning your emergency response. No? Apparently he didn't like the fact. But yeah, it's better not to mess with power plants, nuclear power plants. So pick 2, upgrade without downtime. You need to think, how are we going to do this? So for example, cloud services allow me to go and update the systems, and it does a rolling upgrade. So it leverages basically upgrade domains, and basically goes and everything is good, and I can switch from one to the other with 0 downtime. And that's pretty nice and cool if my application was solely what was running on the cloud service, right? Now, if this cloud service is connected with a database, how do I do 0 downtime upgrade on a database? Any ideas? I don't. So what I can do is I have the system running. I passed my database into read-only mode. I create the copy, do whatever I have to do, and then make it to online mode again. During that time, if I embraced eventually consistent, I could have been doing everything. Everything. Because I didn't lose everything. Because all my requests were in the queue. As soon as it picked up, it started to process. So it's designed for the scale. So you don't know what you don't measure. So try to measure, try to have telemetry. Critical to have telemetry. There's nothing like production. So when you do the integration, testing, staging, production, one of the things is test with at least one of them should be the exact same thing, exact same representation in order to do. So for an example that I'm going to show you is what we did is that we have another, which was a mirror, that we mirror everything that was in production. We upgraded that system, and during a period of time, what we did was we got the load balancer to replicate the request for the current production environment and for the new environment to understand how it was working, because that was critical. That was for updating some of the tablets that people are going and updating applications and so on. So you might need to not get it wrong, or that provider of tablets might not like you very much at the end. So it's very important to do that. So services are autonomous. They need to work autonomously. Try to make everything decoupled. That's one of the secrets that we need to have, is decoupling. And so when we design these things, one of the things we need to have in mind is to design for availability. I need to make sure that my system is always available. And the way we can do this is basically we need to think about decoupling all of the elements. If Yudi Dahan was here, he would say messaging, agree, messaging everywhere, trying to make them decoupled, available, and so on. Try to make it that even if some underlying system is down, I'm still able to continue to do some of my actions. And one of the things which is important in availability is understand your SLAs and calculate your SLAs on your architecture. How many of you have actually dealt with SLAs and calculating the SLAs on your architecture? It can be a very interesting conversation because we go and I was talking with a customer and he was like, okay, so we put this application in Azure. Azure, this is running on a VM. This VM, Azure provides 99.95, so we have 99.95 in my system. Oh, no. Not really. So we have 99.95, but your system is basically composed by one front end, which is a website, which is running on IIS. Then there is an application server, and since you don't have messaging, they are working in series. If one goes down, everything goes down. So that is 99.95 also. And then there is a database that's 99.95. And by the way, you're storing stuff in storage. So that's 99.9. And suddenly, okay, so I need to now calculate all this together, and I get to the number of 99.75 or something like that. And the customer is like, shouldn't this be 99.5? Is that what you need? If it's that you need, now I need to create redundancy in my system. Or I need to create messaging in the middle. Because if I had messaging in the middle, what I could do, the only thing was 99.95. Because the first website, if the other element is down, if he's using a queuing system, even if the server, the application server is down, it wouldn't get down. I wouldn't stop having a system. So I have 99.95 there. And different components in my architecture can have different SLAs. For example, how many of you use BizTalk or TIBCO or something like that? Is an ESB. So it's in the middle of everything. What happens if I unplug the ESB machine? I did that joke with a telco. I was betting with the CEO of a telco that it was so sure that their system was heavily resilient and available that I could do anything I wanted in his data center that nothing will go down. I had done an assessment before, so I knew exactly which machine had BizTalk. And I said, are you willing to bet on it? In 3 seconds, I'll get your system down. And he's like, yeah, do it. I went, pulled the Ethernet cable. That thing went down. You should have seen the phones. And he's like, put that thing back, put that thing back. That's one of the problems of ESB in a SOA 1 type of operation. So in those cases, maybe that should have a higher SLA, a higher redundancy. The other one is scalability. You need to make sure that your system scales. Your system scales. How do you make this system scale? How do you make them? If you have them decoupled, they can scale independently. It's easier. If I have all this completely coupled, when I scale, I need to scale everything. You need to understand what's the scaling units that you have. What's a scaling unit? Sorry?
Something that you clone to create an instance of.
So scaling unit would represent the units that you need to put in order for your system actually scale and be able to receive more connections. And that might be a system, might be a machine. I can say my scaling unit is 1, or my scale unit can be 3 or 4. Why? Because we do performance testing, and we do things like, okay, if I scale 1 more, how's the performance now? If I scale 2 more, how's the performance now? And there will be, at some points, there will be one part that you see your graphs going up and staggering, going up, staggering. So when it stops, when it staggers, that's your element is your scaling unit. And your scaling unit might be in different points. So if my system has web server, application server, database server, and so on, my scaling unit might be, I need 1 of each. Because if I scale only the web, it's not going to solve the problem, because then I have a funnel going into the next phase. Right? Make sense? Okay, data. Then you need to think about the data. One of the things is data. We were talking about SQL servers and talking about how that affects. We need to understand the data. What type of data, what's the speed of the data that comes in and goes out. This is important because we need to understand the data, the latency of the data, and how are we making this resilient. For example, I don't need backups in the cloud because the cloud does that for me. Is that a true statement or not? No, definitely not. I need to do backups because one of the things that the cloud is really good at doing is replicating even your screw-ups. So you go in, like some of my team member did, go into a production database, and for some reason, nobody understands why, oops, I deleted the table. It's pretty good. The cloud's pretty good. It replicates everything. So all the 3-6 replicas that you have now have no table. Do I need a backup? Yeah. I need something to beat up the head of that guy. So think about that. Agility. It needs to be agile. The system needs to be completely agile in order to allow you to have independence on the several systems. You need to be able to quickly turn on a new scale unit and turn off. Don't forget to basically scale up and down. The down is also important because most people remember the rules for scaling up and not scaling down, and not a good idea. Sustainability. It needs to be sustainable. What does this mean? It needs to provide telemetry which is good enough to understand how's the application going. For example, my application should be pushing me the state saying, I'm healthy, I'm doing this, I'm doing that, I'm submitting an order, I process the order, and everything. And that will allow me to understand not at the level of the infrastructure, but at the level of the application, which is what's important for us. Correct? So for an operations person, what's important is knowing that the infrastructure is working, or if I'm, for example, doing a seat allocation project, so I have an application which is for seat allocations on a plane, and my business defined that I need to be able to have 50 seats allocated per minute. What should be the metric that I'm seeing? That metric, the business metric. All the other ones, the infrastructure, application, everything, will be on the next level with alerts and with elements, automated runbooks in order to do that. How many of you have done runbooks or playbooks? How many of you know what a runbook or a playbook is? Runbook or a playbook, when you do a PowerShell automation, for example, you're actually doing an automation, a runbook. A runbook is basically a definition of, if this happens, this is the process that I'm going to take. So a problem happens. So for example, I have a storage account went down. What's my mitigation plan? This is my definition of the runbook. And then I can automate the runbook with PowerShell, Chef, Puppet, whatever I want. That's the concept of a runbook. Okay? So what we can do is create those runbooks. Insights, telemetry, crucial for us to have that. So, and then failure. We need to have this design for handling failures, because that's the only thing we are absolutely certain it will happen. It needs to fail gracefully. So I need to make sure that even if my system, I have messaging, my system was processing a message, everything was going well, and since it's a message, if it doesn't take it out, the message pops back on. So I don't need to do anything else. Agree? Or don't? Do I need to do something else? Yes. What about if, so that thing was basically finishing, it already starting the processing, went down, then message comes back up, and it starts everything again. How's my consistency of data going to end up? Not good, right? So that's what we need to handle for failures. So that is precisely what we need to have, is precisely that idea. So now let's jump to some best practices. Okay, so one of the things is we need to understand what we are getting into first. So part of the architecture, we start with application architecture, but then we need to fit this somewhere. How many of you think about where your application is going to run while you're in the design phase, and not only at the end? It's critical to do that. It's the same thing as saying, hey, we have two parts here. We divide. You guys are going to build an engine. You guys are going to build the outside of the car, okay? And we meet up and we integrate everything. And everything will work well. So these guys go in, do a massively pretty car, sports car, and everything really pretty with an engine, a size for the engine of this big. And you build the best engine you could, and it's this big. Is that going to work? Probably not. Probably not a good idea. So one of the things that, for some crazy reason, who used Visual Studio 2010? So 2010 had a pretty cool feature, which was the diagrams, the top-down diagrams, which I could actually define my topology and say, this is the servers, this is configuration, this is the DMZs and everything. And then I would put in my projects, I will assign to one of the servers. And when I would compile, it will immediately tell me there is a problem with your system because it doesn't fit what you were planning for. That was a brilliant feature for me personally, which for some reason disappeared. I would love to understand that. But it's important to understand. So we now have like A9s, which I have like 112 gigs of RAM, pretty cool. I have these, which are the SSDs, 112, also 800 gigs of SSD drives, all of that. You need to try to target, and the way you decide this is basically what you're going to do. I'm going to process, highly doing processing of images, so I probably need more memory. I'm going to use, for some reason, ClickView. Anybody knows ClickView? Great BI tool. Not going to do any more comments. which needs like 3,000 RAM, so that you probably will go to that RAM. If you don't need, try to target your design to the least possible, because then you have the agility to scale up or down in size as well as number as you need. So if you are doing, for example, MapReduce, if you're using HD Inside, or if you're using Spark, any of you used Spark? Apache Spark? It's pretty cool, similar to Hadoop. It's pretty cool. In that case, you need high memory. If you're doing, for example, SQL Server and you're leveraging the in-memory capability of 2012, then you need high memory. But you need to understand why. So storage accounts, optimization. This will be shared with you. So some of the elements is settings. By default, nagging is on, and expect 100 is also on. So by just changing that, you'll have an increase in performance. Just changing that. Because nagging, it depends on the size of the requests. So if I'm going for big files, then I should have it. If I'm not going for big files, I shouldn't have it. So a little bit of tricks. Enable metrics is always helpful, because when you ask, even if you go to support and say, hey, can you please check if this happened to me? And they ask you, do you have enabled metrics in that storage account? No. So yeah, you didn't. So there is nothing we can do. Access, you share access signatures, and then from a design and implementations, distribute across partitions. One of the things into a storage account, we have tables, blobs, and queues. So in tables, I have a partition key. So the partition key, I need to understand exactly how my system, my data is being viewed, so I can partition it. Because the smaller the partitions, the faster it gets to do the indexing. Now there is, how many of you have checked DocumentDB? No? You should check. It's pretty cool. DocumentDB. Similar to Mongo as a service in Azure. It's pretty good with Azure Search. So then, in terms of density of blobs, this is some of the limits, so you need to understand the limits. And as an example is, in terms of density, when you're doing uploads, you should do parallel uploads. It allows you to do parallel uploads. But you should also tune with what's the threshold, what's the bytes that it's going to send each time. And that depends on what? Your internet speed. Because then, you can go like, for example, I have a system which I only had to upload 50 gigs into Azure storage. And I placed and drag and drop, I use the tool, not going to say the name, drag and dropped, and a very nice progress bar saying this will take 1,600 and so many hours. And I'm like, what? This doesn't sound right. So I went in and did a small console application in order for doing the upload. Parallel upload, tuned on that. In 30 minutes, the 50 gigs were in the cloud. A little bit of difference. So play that, scale, simultaneous uploads. Make sure, and one of the things is you have a max bandwidth on the blob. So make sure that if you're doing parallel, you don't go over it. Because you know what happens afterwards? You're misbehaving with your peers in the cloud. So you get throttled. And then it will take more time until you behave. So always think about those elements and transient connections. Sometimes I'm connecting and that storage, that NAS went down. I need to be able to retry to another element. As an example, so I'm connecting. How many of you have used the transient fault handling or also known as Topaz. Yes? Transient fault handling application block, very good in order to provide you this. You need to really think what you want to do. Because depending on the error, you might actually not want to go back and retry. That's what this is doing already. So if I have retry logic and basically I try to connect and I get the 403 or a 404 or something like that, it doesn't matter if I reconnect 5,000 times. I'm not permitted to connect to the damn thing, or the damn thing isn't there. So this is what the transient fault handling does. Okay, so example in terms of table, density, partition selection is critical. On terms of scale, partitions, the max is 1K elements per partition. So I need to make sure that. And if you have 1K, you'll see that when you try to go to search for something other than partition or row key, that's probably to be challenging. So think about that. Again, transient faults. Then you have the queues. Density, it's a pipeline model. First in, first out. So it's a queue dispatching service. So you need to think that there's a single queue. One queue represents one partition. One queue represents one partition. If I want partition queues, I need to use service bus. In Azure Storage, which is, I would say, kindergarten level queues, I have one partition is one queue. If I put 1 million messages into the queue, I'll probably turn the damn thing down and get throttled. If I need that, then I need service bus queues with partition queues. Make sense? Multiple queues in order to, and multiple storage accounts. One of the tricks, for example, now it's not needed anymore because of the SSDs. But before, in virtual machines, one of the tricks in order to get more IOPS was to actually say, I'm going to have multiple different VHDs. I'm creating data disks on multiple different storage accounts. I'm going to bind them into that VM, and I'm going to stripe them together. Because they were in multiple different accounts, so I was never going above the limits that I have. So I had the full storage account capabilities to one single file. So I was basically exponentially growing the number of IOPS that I could get. So some tricks. And now, real life. How do we create a highly scalable system? What would you think highly scalable system would look like? Is it an ACID type system, all synchronous? CQRS to the rescue. So I did a little bit of playing around and creating an architecture diagram. So CQRS, clear, it's common response, responsibility segregation. Common query responsibility segregation, right? So I'm clearly separating, this is commons, this is queries. So anything that does an operation, a change operation, it's a command. Anything that wants to retrieve anything, it's a query. And they are actually independent. They are completely decoupled. What I use is, the typical concept is, I will have a client, which the only thing is, receives the call from the service API, and says, let me transform this from an API call, a post or a put or whatever, into a comment. A comment is basically, how many of you know event hubs, Azure event hubs? How many of you Azure Service Bus? Good. Service Bus, queuing system, rock solid queuing system. It's not kindergarten anymore. But what it provides is massively scaled partitions and so on. Then they just released event hubs. What is event hubs? It's something that is being used by Azure Intelligence System for IoT. It's a massively scalable queuing system. I can have millions of messages flowing into that system. That's what event hubs is. So, and then our event bus can be dependent on the number of events that I'm expecting. So if I'm expecting to have like 1,000, service bus is good enough. If I have like 5 million, then I probably need the event hubs. If I want several billion, then I'll probably be implementing at the level of UDP, because that's where you can get that speed. So this is basically our bus, is where all of our messages are going through. This message is basically a command which is wrapped. So imagine this is a post product. So post product gets transformed, and it basically creates here a message of type add new product command, which has all the information that I sent into my file. Then what it goes is those command handlers, using here a microservices strategy, we have micro things which are only concentrated on doing a single unit of work. So what he's going to do is look at this event bus and say, hey, I'm only interested, you can have multi-million of things. The only thing that I'm worried about is that add new product command. So it subscribes to that, does whatever it has to do, and while doing it, the way we can get telemetry in real time is that while doing it, is sending events back. Things like, I started processing the ad, I ended processing the ad, processing add product done, and things like that, several types. So I'm feeding the information. And then, this is all through a domain-driven design kind of approach. And then I subscribe to the events that I want. Can I have 5 million different events being fired? I just want 3. Make sense so far? Then I use event sourcing. What's event sourcing? Is basically storing all the events that happen in the exact same order that they happen. So this is my single source of truth for the system. What happens is, by doing this, my system immediately becomes resilient. Why? Imagine that something failed in this. I want to replay. I just take the commands from here, shove them back here, and the same result comes out. How cool is that? Do I need backups every hour? No. I have backups. Imagine that I have a database somewhere here. What happens is, I do backups every day, for example, and I have this replicated in 3 different locations. If this database is lost, I basically put the backup there, and I replay today's events. And everything goes back. I never lost a single thing. Then the only thing I need to worry about, what's my recovery point objective and what's my recovery time objective, right? So, and this is on the command part. But then we have, but what happens if someone wants to see this? So if I have a get list of products or a get product by ID, don't I really know what the response should be like? Right? I know. I know how the response should be like. And when it should be actioned. When I have a new product, if this guy, my denormalizer, also known as projection, if he's searching for that execution event, which is new product added, if I subscribe it and have the query definition saying, hey, the result is I have several views that I have. I have the list view. In that case, I need to add this new element into that pre-prepared view. Or I have a by product, and I pre-prepare that. And this view data can be, in the example that I'm going to show, was actually a JSON file already made. So as soon as someone would ask me, hey, give me for product A, I already have the JSON. The only thing, there was absolutely zero processing. The only latency, the only time that it would take in order to serve was the time to receive the element and about 1 millisecond in order to shove the response back, because it was the time to connect to the storage account. So that was the speed that we could get and serve responses. Does that make sense? Am I completely crazy? Who agrees? I agree. Okay, so benefits are allow us to easily scale the backend. So since everything is async, I can scale independently. For example, in this case, we created, the case that I'm going to show you, we created different priority elements. So we had pri1s, pri2, pri3s. And instead of putting all the denormalizers on the same service, we basically put them in services pri1s, pri2s, pri3s. And so basically I have different scaling units for all of them. So if I want to scale my pri1s, because they were a group, I would scale them and I would make fast. So for example, if I want, there was a specific kind of view that I needed quicker, I basically would scale my pri1s, and that means that that is quickly or quicker to get the result. So I would have latencies like 1 second or something between a command coming in and the view being available. Can we work with that? Probably we can. Most of the business can. The second one was compartmentalized logic. Everything is compartmentalized. Have any of you read one book, which is pretty cool? It's a small book, but it's pretty cool, which is Simple Solutions for Complex Problems. How do you eat an elephant? Poor little elephant. No elephants were harmed during this recording, by the way. How do you eat an elephant? Come on. Piece by piece. So how do you process, how do you compartmentalize your complexity? This is very complex. I have to go through all the stages. You already compartmentalized. You already describe which stages you need to go through, right? So what you do is precisely that. You define the microservices strategy, which element is very small. And this was, I did this with a team that never had heard about CQRS, so it was pretty cool. So the only thing is I gave them a framework, and I said, this is what you need to do, some templates in Visual Studio, and this is what you need to implement. If you look at your command handler, and if it has more than 10 lines of code, you're doing something wrong. Because it should be, if I have something that would require like 50 lines of code, it means that I can compartmentalize that. And one of the things that you can do, I will show you how. You can also create correlation IDs, which is pretty cool to understand what one command started across the board, which is also very good. So all the audits. So this is a real example implementation of this. I have a UX, an admin UX. So the customer, this was for backend of a device, so a tablet device that needs to receive over-the-air updates, right? Pretty important. But also, what else happens in devices like this, or an iPhone, or an Android, or anything? What else happens in here? I have one of those devices. Is there a device tracking information that gets sent to the server? No, right? That would be privacy violation. As long as it's anonymized, yeah, there is. Another thing is also crash dumps. Remember one thing. This is a sensor. It's a device. Internet of Things. Everything is connected. How many of you use GPRS or are always connected? Most of us. Welcome to the new world. I can understand what you have, the problems you have, before you even know it. Because that thing is going to send. So it continuously feeds information about things like the device tracking. Anonymously, what are you doing with the device? I'm turning my machine over and doing something. That information I can receive. And the service needs to receive that. So what we need is, we had a place for someone to go and place a new firmware and say there's a new firmware update. So he could do and add a new firmware, edit or replace one, delete one. And this is the commanding part. So what happened is, we have here the domains defined. Domain-driven design. What's my domain? It's a firmware. It's an update. It's an application. It's my domain element, my model. Then I define what was the commands. What's the commands? Insert firmware, update firmware, delete firmware. Right? And so this is the command handler. So this guy goes, receive one of those, transforms it into one of those commands and puts it inside, in this case, event hubs. This guy, the only thing that knows is, and it's cared about, is I want to subscribe to the insert command, insert firmware command. Basically, you subscribe. As soon as it receives, it starts processing, which is, in this case, it shoves something into a configuration table, just drops a line there, and sends events saying, I started, I ended, and all of those things. And then we go. We have here the event store. In this case, we're using view stores. As this guy uploads, he uploads into one of our blob storage, the firmware. We are fronting that with CDN. And basically, when a GET comes, the GET, the only thing is, based on the GET, the query service, this guy here was subscribing to the insert firmware done or completed. Can't remember the name. So he subscribed and it generated immediately a JSON file, which is the response for any kind of device, because that's the latest firmware. So any device should receive that as being the latest one. If you're in the latest version, you receive nothing. If you're not, you receive this one, right? So we created the JSON file, which was the response. So this guy, as soon as the device says, is there any firmware update for me? The only thing this guy does is pointing and providing the contents, providing this file as the response back. How? Basically, we created here a pattern of generating the name of the file. So device, imagine I have my surface, surface1 underscore, what's the type of response? If there are different types, I could have type underscore the response. It's a JSON file. It's already ready. Our web APIs return JSON. The only thing I need to do is, it's like when we go to a public station. They have a lot of papers, and there's someone always just going like, it's exactly what he's doing. He doesn't, I would say, is almost brain dead, that guy there. He doesn't know anything about how to generate the views. He doesn't care. You just need to feed it. Does that make sense? So this was the architecture that I was telling you about that went from 200 concurrent users to 10,000 with the same level. Because then you can play around with things like, okay, right, so if I have thousands of devices connecting at the same time and they all receive the same response, I don't go to that thing every time. What do? I leverage the HTTP cache header in order to say, cache this in here in the client for a period of time. Because for me, if you don't receive the greatest and latest version in the next half an hour, it's not a problem. So I cache that. and it's even faster. So even this round trip is not happening. So is how creative you get. So in here is an example. So I'm inserting the UX inserts. We basically go and transform the service client, transform it's called, with the publish of that command. Basically, we select, we put the message in, then the command handler picks it up, starts to feed the events. Events as an insert command, it's not very, let me see if I can, without destroying anything. Yeah, now it's visible. So one of the things that happens is there are 4 types of events in event-driven architectures. Who knows what they are? Execution. One thing, I did one thing. Life cycle, I started, I ended. There is business, because what's the events that are important for the business, and there is the operational. And in this case, we have here insert firmware, started, insert firmware, ended. So I have my life cycle. Then I have some execution events. In this case, I tried to put here a stage approach. So in order to do an insert, I have multiple stages. In order to use microservices and to reduce complexity and reduce the potential of someone writing really bad code, we basically separated those in 3 stages. So that message, actually, that command actually sends a subcommand into the system, which then gets picked up by this. Then what happens is it gets validated. There are execution commands, sub-execution, and there is a main execution command saying that insert firmware, completed, done, whatever. And then there is the operational events. Operational is normally anything that is with third parties. So infrastructure, or I'm connecting to storage account, or I'm connecting with Service Bus. When did it start? When did it end? How many times it fails? How many times did I retry? Why is this important? Now I can do search on a pattern, and if I failed more than 5 times over a period of time, I can act with my runbook. My runbook is what? Is a command handler, which is looking at that specific pattern. So by doing this, and then the second flow, which is when we are processing it, so the projection is subscribing to the main execution event, is generating, so basically picks up, feeds it into my domain model, and then serialize it to JSON. What we have is, we have now the JSON file done. And now, everything is prepared. When the device calls, immediately get the response. There is no absolute processing whatsoever. And this handles several things. One is complexity. Why? Because I created microservices, and the complexity is really low in every single piece. So it's really easy for you to find yourself in the middle of the project, because you know exactly where things are. Also allows scale, because every single piece can be scaled independently. And if I need that my response, I need to optimize to reads, I basically spin up more elements, more instances of the projections. If I want to optimize for writes, I basically scale my command handler's elements. So it's completely elastic end-to-end. And it's also completely decoupled. If I go in and calculate here my SLA, the only thing, because this is a wrapper class which is running on the API, the only thing that I have here is my API and my service, my event hubs. And my event hubs, it's not still in production, but when it comes, it's probably going to be more than 3, 4 kind of nines. And so this is how, with a solution, so the deployment of this thing to end up to support about 5 million devices, how much do you think, how many instances do you think we have in all of the system? Give a number. Come on. Like we do estimations.
There's probably about 20 moving parts.
There's about 10 instances overall. There's a lot of other moving parts, yes. But what we did was, at the end, since they are decoupled, but I can join them together where I want. So we had them completely decoupled. It was like 20 different elements, 25 different elements. We placed more than one thing in the same box because we wanted to optimize at the same time for cost. And we have about 10 instances. And actually, for the 5 million, if the 5 million decide to hit me at the same time, I only need about five webs in order to support it. Gives you a perspective. The cloud is not only about, oh, the cloud is disrupting, I need to do things differently. No, the cloud gives you the ability for you to think about the problems in different ways. It's not that you wouldn't need to think when you are on-premise, is that there was no visibility of all the costs that were involved. And there was one thing which cloud is really good, is putting in your face how much you're spending for a specific application. And that is going to be shoved in your face, I'm pretty sure. That's been sometimes shoved into mine. Like, why is this costing us so much? This is not business critical. Oh yeah? So wait for the next turn. You'll see what happens. Now is the other way around. Is, okay, Mr. Customer, I cut you this much. So you were using, before this, you were paying this. Now this is what I'm paying. So instead of paying me for the project, do you want me to give me the difference? Like you were at the start? And it's like, no, let's not go there. That's not a good way to look at things. I was joking at the other time. Yeah, of course. We are all joking. So to finalize, some lessons learned. Instrumentation is key. Custom performance counters, timings, trace logs, they are still important. Most of all, telemetry. If you use something like this CQRS approach, if you not used to CQRS, there is CQRS journey you can look at, cqrsjourney.github.io, I think. It's a project. That has a book and has also a framework. The framework, there are a lot of frameworks out there. Low-code CQRS, which is a very simple. Greg Young has a couple of frameworks, simple. If you want all the capabilities of replay and everything, CQRS is definitely one of the best out there. And this was from Microsoft Patterns and Practices. And if you think about, oh, Greg started with the CQRS, yeah, Greg, Udi, there are in those books. If you go to the book, you should see who the analysts or helpers for Microsoft in that. You'll get people like Greg Young, Udi Dahan, and I was one of them also. And there were more. I think there were more that are here speaking, which are part of that. So it's not something that Microsoft made up and true. It's something that went through a channel of a lot of discussions. And when I say discussions, is a lot of discussions in order to get there. Watch trends over time. Critical. Don't look. When you're seeing performance counters, don't look at the 5 minutes. Don't look at the last 10 minutes. Look at hour, days. You see the trends. You can't see anything in 5 minutes or an hour. You see based on trends. There are minimum memory leaks that you can find. Profile your code, that's important, and that's why we were doing all the events. Build for scale. Optimize for reads, optimize for writes. Make it independent so you can use this. And so those are the strategies. And most of all, have remediation strategies. You need to remediate, weight your risk. What's my risk? I want 5 nines. Okay, why? What's your risk? Let's measure that risk. And let's see, if I do A, this is the risk. If I do B, this is the risk. Can I handle this risk? If the business can handle this risk, then you create the compensating strategy. Always analyze that. And do geo-distribution, multiple data center. If you're a global business, probably multi-cloud will also be important. So this is the strategy. You need to think, design, thinking on the cloud, thinking massively scaled. You're not alone in your cloud provider. You need to have scale. You need to be absolutely decoupled. And you need to think outside the box. Completely think outside the box. If you do that, you'll be successful. Thank you. Questions?
Do you have an opinion on, recently Azure brought out a management portal for managing private cloud in a similar way, on-premise?
It's part of the Azure Pack. Part of the Azure Pack, yeah. So Azure Pack is pretty interesting. It doesn't have the full features because Azure Pack brings more the websites part. But now it's what they are bringing is the new integration. So there was a release of System Centers, the new versions, which provides as the application controller, I think, which provides a similar type of approach. I would say it's the right approach. So if you think about the Cloud OS that Microsoft is there yet. It's not perfect, but it's pretty interesting in order for you to manage that on-premise also.
So for those businesses not wanting to go to the public cloud, is it a good enough alternative?
Yeah, it's a good enough alternative right now. So if you leverage things like the Hyper-V, System Center, if you need Service Bus on-prem, you won't get Event Hubs because what Event Hubs basically is Service Bus with a lot of networking optimization. So you get Service Bus also out of the box. You have the VMs, the same capability, and you can manage with the exact same tools. If you leverage a System Center, Orchestration Manager for the runbooks and all, yeah, it's a very good alternative. I've worked with several from VMware, from Microsoft, and it's very good. It's completely different from a couple of years ago. More questions? Was the session helpful? Good? According to the expectations? Good. So thank you again for coming. If you have anything, just pop me an email, go to the blog and put some comment. Or in Twitter. You can just insult me on Twitter, as usual. So feel free to do so. And if we have also the Azure user group, if you don't know, there is an Azure user group, several presentations, so it would be interesting if you want to know more. So great to see you. Thanks again, and don't forget to fill the evaluation form, and they will beat me up. Thank you again.